So I'm Rob Cunningham. I'm the executive director of the Pittsburgh Quantum Institute, and I have the great pleasure of introducing our next speaker, Travis Humble. Travis has many roles. Let me just mention two of them for you. He is the director of Oak Ridge National Laboratory's Quantum Science Center and also the Oak Ridge Leadership Computing Facility Quantum Computing User Program. So let me take a moment to welcome all of the high school students that have come here to hear him speak, in addition to the regular members of the Pittsburgh Quantum Institute. For the high school students, Travis has been in charge of the most powerful computers in the world, and he and many of the scientists that he works with have had a number of just incredible breakthroughs. For you, high school students, but also for the PQI members, I suspect that some of you, maybe many of you, will remember a Nature paper from just a couple of years ago that he co-authored entitled Quantum Supremacy Using a Programmable Supercomputing Processor. When this paper was released just a couple of years ago, the entire scientific and computing worlds stopped for a little while to understand what the implications were of this paper and what the impact of the breakthrough itself and the breakthroughs that were to come would mean for humanity writ broadly. That was just a couple of years ago, but Travis has been doing a ton of things still. He continues to explore quantum computers based on different types of qubits and different architectures. He's achieved numerous other important algorithmic and application breakthroughs. And in addition, he helps others achieve scientific advances. He serves as editor-in-chief for the ACM Transactions on Quantum Computing. He's the associate editor for Quantum Information Processing and the co-chair of the IEEE Quantum Initiative. Today, he's going to tell us about unraveling the mysteries of quantum science and technology. So help me welcome Travis to Pittsburgh and to PQI.
Hello. Implications. I picked that up from what Rob was just saying. I could have titled this Understanding the Implications of Quantum Science and Technology just as easily. But I thought the idea of unraveling the mysteries might spark a little bit more interest. Everybody loves a mystery. The scandal, the intrigue, the discovery. I've got like 2 of the 3 there, so we'll see how this goes. But the reason I wanted to focus on this topic is that 2025 has been declared by the United Nations as the International Year of Quantum Science and Technology. So trying to understand why would they do that? Why is this year so important is going to be the starting point of this discovery. This is the type of people you would like to invite to quantum mechanics' birthday party. These are some of the most celebrated scientists from a century ago, including Albert Einstein, Marie Curie. There's 2 in the back here, Werner Heisenberg, and Erwin Schrödinger, who actually in 1925 composed 2 fundamental papers that outlined what we now refer to as quantum mechanics. That's one of the reasons 2025 is the 100-year anniversary and the International Year of Quantum Science and Technology. But what were they talking about at the time? They had just come out of a period where people had thought that our understanding of physics and all of the world around us was a little boring. They'd recently uncovered some departures from that understanding that led them to propose a radical new theory where the elements of the universe were actually quantized. That's where quantum comes from. It's a really different way from how we think about things today. Typically, if I'm out in the classical world, as we call it, my intuition tells me that cause and effect has a very linear relationship with my surroundings. Think about billiard balls. If I'm lining up for a shot on the pool table, I can easily calculate the trajectory of how I need to hit that cue ball in order to put one in the pocket. Turns out I can't actually do it very well, but I can think about the calculation necessary to make that happen. This new theory, quantum science, actually introduced a fundamentally different aspect of the nature of the reality around us, and that's this wave-particle duality. These cue balls and the billiards that we work with were no longer described as point-like particles, but instead they had a new nature to them that led to things like interference and superposition that were radically different. The development of that theory, the quantum physics that could describe these things, including at the very small level, was the essential breakthrough that happened 100 years ago. Let me give you an example of this. Almost all of us learn about the hydrogen atom, starting with the picture that you see on the right. It's almost like a solar system model. In the middle is a proton that represents the central element, and around that is orbiting an electron. But there's some immediate concerns about this. If the electron is negatively charged and the proton is positively charged, why don't they immediately collapse upon each other? What prevents that from happening? What you see on your right-hand side is the picture of what quantum mechanics tells us a hydrogen atom actually looks like. It's not the simple orbital description that we might get from a classical understanding, but instead we now recover what we call modes of the hydrogen atom, or its orbitals. And these orbitals are very different from the ways that we've previously been thinking about atomic systems. And while these may look like pictures, we can actually now experimentally validate that in fact hydrogen atoms and many other atoms and molecules are fundamentally different from the classical descriptions that we thought were right 100 years ago. This is actually an experimental image of where the electron would be located in a hydrogen atom, and it actually corresponds very well with one of those expected orbitals. Now, that plays an important role in many of the technologies we use these days. If you're familiar with lasers, you'll know that those are sources of light, but what's unique about them is they can actually have very well-defined frequencies. The energy itself can be what we call coherent, which is to say that it is synchronized in a very distinct way, and all of that traces back to the fact that the atoms themselves have this discrete quantized structure that enables us to access the energy from them and perform these types of technologies. So there's an immediate implication. I would have called it a mystery. How the fundamental nature of the universe, the constituent parts that make it up, are radically different from what we would have originally thought based on just of our classical intuition. But it has many other implications as well. Medical imaging is an extremely well-known example where we use the quantum mechanical properties of individual atoms, in this case their nuclei, to actually probe them with relatively strong magnetic fields in order to map out the density of water and other liquids in your body. That's an important breakthrough that could only have been made through our understanding of how quantum mechanics actually describes the world around us. But things do get weird. This idea that we can actually prepare synchronous, coherent superpositions is something that leads to certain paradoxes. Take the atom again, for example. It contains energy, and in many cases, radioactive elements actually decay and release that energy. But the time at which they decay isn't pre-described. In fact, in this particular case, the blue box you see up there is a source of radiation, and at some point in time, a particle will come out of that, hit a trigger device that actually breaks open a vial of poison, and in this somewhat contrived scenario, there happens to be a cat next to the vial of poison, and they're all enclosed inside of a box. For an observer who's external to the box, unable to see the cat, unable to see the vial of poison, or whether the trigger's gone off, or even whether the atom's decayed, we now exist in a period of uncertainty about whether the cat is alive or dead. And Erwin Schrödinger, who we saw in the birthday picture earlier, was actually the person that came up with this, and so it's referred to as Schrodinger's cat. And the paradox is that, well, how can a cat be both alive and dead? How can there be a superposition of these two seemingly disparate outcomes? And it all traces back to the question, did that atom decay? Did it release this packet of energy that caused that chain reaction? And quantum mechanics says, well, I can't tell you that answer exactly, but I can give you a probability that it occurred. And if you wait longer in time, then yes, there's a higher probability that the atom decayed. But at some midpoint, there's actually a genuine uncertainty about whether the cat is alive or dead. Now, if you've ever tried to put a cat in a box, you understand there's no uncertainty about this. The cat will most certainly let you know that it does not like this situation. But Schrodinger was trying to provoke the idea that the consequences of quantum theory are not so simple as making radical technologies, but instead there's other fundamental mysteries here about how the world operates and how it affects us. So, for example, if you were to imagine that definitely one of these outcomes has occurred, either the cat has died or it's still living, then at any given point in time, you may imagine there's a divergence in our representation of the world as a real, fundamental, tangible object. This divergence you can see here is kind of the film strip forking off in two different directions, has led many to think about what they call the many worlds interpretation. What if there are alternatives to what you're experiencing right now? And what if those alternatives trace back to the idea that quantum mechanics itself does not give us that prescriptive expectation for how the world should behave? Now, many people look at this and say, well, the truth is I can only take one branch at any given point in time, and that's always going to be the branch that's most important to me. But the implications of this are that superposition and the ability to create these alternative pathways is a powerful technique that distinguishes quantum theory from the classical world that we're used to. It's something that we can actually test, though. This is an example of a particular type of drum. It's actually what do they call a mechanical oscillator. This is aluminum that's been laid on top of a silicon substrate, think of glass. And it's about the size of half of a human's hair's thickness. But even at this small of a device, which is certainly bigger than any individual atom, we can observe these types of quantum mechanical superposition effects. You can actually make it so the left drum and the right drum are entangled with each other. Their behaviors are correlated. In the same way that those two worlds in the film strip split off into different directions, we can actually create a superposition of possibilities where the left drum and the right drum are beating in sync or out of sync with each other. And the ability to manipulate these objects, even at this relatively small scale, opens up new pathways to creating new technologies, new sensors, new computers, new types of processing information. Now, this has been a fundamental discovery. In the past 100 years, we've not only gained more insight into the periodic table and all of the elements beyond just hydrogen, but also into the fundamental nature of the protons and neutrons and electrons and other fundamental particles that create everything around us. And for my high-energy physics friends, this is known as the Standard Model, and there's key questions right now whether the Standard Model is actually complete or are there things yet to be discovered. But just having those fundamental building blocks at our fingertips gives us pathways to creating entirely new technologies, including the medical imaging we were talking about, the lasers that we find everywhere, and then, of course, the possibility of using those and accessing the most powerful the most powerful sources of energy that the world has ever seen. Nuclear weapons have always been a scary topic, but they're a direct consequence of the discoveries that we've made in quantum theory over the last 100 years. They have benign uses, including the development of nuclear reactors and long life nuclear engines. example in deep space probes. But even such a minor change in our theory, taking a hydrogen atom and no longer drawing it as a circular orbit, but instead quantizing its energy and giving us access to this intimate structure, has enormous impacts. And for me, that actually led to the establishment of Oak Ridge National Laboratory. That's where I work in Tennessee. It's a Department of Energy facility now. This is what it looked like 80 years ago, just 20 years after the discovery of quantum mechanics and the translation of these ideas into some of the fundamental technologies that we use today. It's blossomed now into what we call a multi-science facility, not just looking at nuclear reactor technology, but looking at computing, information, materials, chemistry, you name it, we probably work on it. But one of the things that this intersection of many different disciplines has raised has been a curious question about what does it mean for this theory of physics in the context of describing materials and atoms and light and all those other physical quantities. What does it mean when we start thinking about information? Now, this collection of pennies is intended to represent the zeros and ones that I think we're all fairly used to at this point. 100 years ago, that would have been an absolutely bizarre statement to make. The theory of information was not yet worked out. The idea of quantifying information as a fundamental principle of our environment was not yet worked out. Now we talk about bytes and bits and bandwidth all the time. But back then, they were waiting around for somebody to come along and discover that. But some of the key questions that they're looking for here are things like entropy. That's a measure of disorder within systems, and you can imagine a collection of pennies like this seems relatively disordered. In fact, you can prove that it's the most disordered it could possibly be. This idea of an entropy function, where the bottom axis there is a measure of how fair my coin toss would be. If my penny could give me heads or tails and I flip it, well, if heads is 50% of the time, I'll actually maximize the energy. That's the peak you see in this figure. Now, if I'm a magician and I'm using a tricked out coin, I can actually make it so it always comes up head. I've minimized the entropy. I've minimized the likelihood of any disorder in that outcome by ensuring it's always going to be one specific thing. Claude Shannon was a pioneer in the field of information theory. And similar to how our guest at the birthday party pioneered our understanding of physics and the world around us, Shannon came in and understood that information was fundamental to how we exchange communications, how we talk about computation, and ultimately how we gather information about the world around us and assimilate it into our own lives. Now, he also made some bold statements about what information is. He took advice from several people, including John von Neumann, who's one of the pioneers in computing, when he pointed out that you should call this entropy, just like we were talking about a second ago. It's already being used in the field of thermodynamics there. It also represents the idea of disorder, but nobody really understands what it means, so it's a great thing to use here in information as well. It turned out to be a great idea, and the reason for that is there's an extremely strong connection between the disorder we think about in physical systems and the disorder we think about in information theory. Now, there's been a lot that's happened with information over the last 100 years. Back in the 40s, they started to create this new type of device that we now call a transistor. It was actually motivated by radar applications at the time, but it quickly became recognized as a fundamental way of switching back and forth between two levels of signals. That becomes a fundamental way of trying to express zeros and ones. We've now translated that technology to where we can create trillions of resistors, even in devices just like your cell phone. That's an enormously powerful way of creating fundamental units, combining them together to enable a new system-level representation of what information is. And of course, that now dominates our world. So you can't escape the digital age because this has become so pervasive. But it all traces back to Shannon and his recognition that information is a fundamental part of what we're trying to do when we interact with the physical world around us. So let's take a moment and think about what we've said. We've talked about this 100-year anniversary of quantum physics. Quantum mechanics is a framework for describing the elements of materials and molecules and other forms of matter. And then we've talked about this important part that information is a way of expressing everything around us. Well, when you start to merge these two paradigms together, and this is the essential thing that's happened over the last century, you recognize that information is inevitably physical. And what I mean by that is, of course, the sound of my voice right now is propagating through the air, compression waves, your eardrums are picking it up, translating that into electrical signals that are processed by your brain. Visually, your eyes are picking up light that's reflecting off that. Yeah, that's information in a physical context as well, but the limits that we place on our ability to reason about that information are then ultimately tied to the physical platforms in which it's being expressed. So, if I live in a classical world with billiard balls and other types of objects that I'm familiar with, I'll have limitations on the way I can process that information. But if I translate over into a quantum world, where quantum mechanics is now dictating what is physical, then this statement becomes information is inevitably quantum physical, and that has radically different consequences. Now, just to emphasize this again, we've talked about how we can create superposition, how we can bifurcate into these alternating worlds, how we can entangle things so that their behaviors actually become correlated with each other. You could ask, and this is a legitimate question to ask, is, are you crazy? Because some of those things that we're talking about defy our intuition. If you and I are entangled with each other, let's say we're the two elements that you see in this picture, then our behaviors actually correlate regardless of where we are in space and time. I could be on the other side of the river, the other side of the world, or the other side of the universe, and quantum mechanics says that we're going to be in sync with each other. John Bell, back in the 70s, took that question seriously. Are you crazy? And he came up with a test. And they call it Bell's test today. But what he said was, well, let's imagine a situation where these particles are very far away from each other. Are there things that I can do that could discriminate between quantum mechanics telling me the truth and me just not really knowing the real story? Maybe there's a local hidden theory, maybe a variable of some sort embedded in the reality in which we live that I just haven't uncovered, I haven't discovered yet, but it absolutely does not require all these crazy assertions that quantum mechanics seems to make. He says it, perhaps nature is not as queer as quantum mechanics. But Bell's test went on to kind of change the outcome of that question. As he puts it, the experimental situation is not very encouraging from this point of view. It's kind of an undersell of the fact that he developed a test that can actually discriminate whether our world is quantum or not, and our world repeatedly has passed that test as being quantum. This is difficult to refute then, that all of these considerations, all these mysteries and the consequences and implications of quantum science and technology don't actually exist. Yes, we have the technologies we've developed, but there's always a possibility we didn't understand what we were doing. With Bell, we now recognize that the evidence is overwhelmingly in favor of quantum mechanics being the correct description of the world around us. Now, we're going to have to live with that. And the consequences of having to live with that mean that how do we actually use these ideas to better our own lives? When you look around nature, you can actually find a number of instances where quantum mechanics is not only important to our understanding at the scientific level, but also impacts the technology and the developments of our society. Take high energy physics, for example. How do fundamental particles interact with each other? They scatter off, they consume and create and destroy. That is exactly the types of processes that occur within the sun, which I would argue is probably the single most source of energy for our entire planet. Our ability to understand the sun, as well as other fusion and fission reactions, plays an important role in our ability to create new energy sources, to mitigate the effects of radiation, as well as to understand what are the fundamental fabric of the universe around us. Superconducting materials is something that we've been talking about a lot. It is also an extremely powerful way of being able to transmit energy. Superconductivity means there's no resistance to the transmission of electricity. That is an important concern at the moment because many of the electrical wires that we have installed already actually dissipate energy, create heat, and therefore become an inefficient way of distributing power. But if we can understand the principles of superconductivity so that those types of materials could be used more broadly outside of experimental laboratories or extremely cold environments, then we could create fundamentally new technologies that gave us access to ways to not only generate information more efficiently, but distribute it more cleanly and more reliably. This third picture is actually a chunk of aluminum. It turns out to be an important catalyst for many chemical reactions. But the ability to understand how that catalyst actually works depends on the reaction that we're interested in. Quantum mechanics is fundamental to the description of chemistry because the electrons and atoms themselves are undergoing changes. The dynamics of how they behave requires complex calculations in order to model and understand them, but then more importantly, to create new technologies that can take advantage of that, including things like batteries that are able to convert from different chemical energy sources into stored energy. So we've got a good set of problems where quantum mechanics appears and, most likely, could be useful in the solution to them. About 40 years ago, someone made the rather significant point that if you want to make a simulation of nature, and we do, just like the examples we've been talking about, we want to be able to mimic the behavior of nature so that we can gain insight into it, so we can design and develop it, and ultimately so we can create new pathways. But if we want to do that, Feynman says, you'd better make it quantum mechanical. And he's not telling us that the models and reasoning that we need to use is quantum mechanical. We've already addressed that question. That has to happen. What he means here is that the technology itself needs to use quantum mechanics to solve these problems. How are you going to solve the mystery unless you have all the clues available? In this case, Feynman's point is you've got an important clue, which is that quantum mechanics is the answer. But you're going to have to start creating things that can make use of that. And this is not an easy problem. In fact, for over 40 years now, people have been trying to realize this paradigm that quantum computers, methods of simulation that use quantum mechanics at its core, can actually be created. Now, just for a little bit of jargon, because I'm going to probably start using the word qubit unintentionally, we talked earlier about binary units of information, or bits. In quantum computing and all of quantum science and technology, there's a corresponding idea of a qubit. The qubit, or the quantum bit, is typically represented by the sphere that you see on the left. That sphere has a north pole and a south pole. And in the extremes, the north pole will represent the number 0. So just like a bit, we'll have a 0 representation. And at the other extreme, at the south pole, will represent the number 1. Now, if this were a binary system, a bit, I would only have 0 and 1 as the possibilities for my information. It's either one or the other. But as we talked about earlier, quantum systems actually can have superpositions. So every point on the surface of this sphere is actually a valid qubit. So that's to say, if I wanted something that was half 0 and half 1, I could pick something along the equator. In fact, there's multiple points along the equator because in addition to having the idea of being half 0 and half 1, I have this coherence that exists between those two elements, and that's represented by the imaginary phase that describes the position on the equator. So a couple things to emphasize here. There is an infinite number of points on the surface of that sphere. Again, my binary unit of information has two values. It's either 0 or it's 1. My qubit has an infinite number of values. That's a remarkable distinction. But if I want to build a quantum computer, I'm going to need way more than one qubit. Every individual qubit is going to be necessary to represent information, but I'm going to need an array of those qubits connected together in which I can perform operations on them correctly. And I can string those operations out long enough that the information in that system is not lost. We were talking earlier about the radiative decay of some atoms. With my qubits and the technologies that we use, many times that energy will dissipate and I'll lose that information. So this lifetime of information is an important way of ensuring they stay coherent. And then ultimately, and this is kind of weird, but ultimately I've got to translate the information that's stored in my qubit back into the real world. I've got to make a measurement. I've got to do this conversion from quantum back to classical, and that's going to raise a lot more questions. But this is kind of the jargon. So qubits are the fundamental units of the technology that go into quantum science. And there's many different ways to make them. One of the popular ones is to trap those atoms we were talking about earlier. Not just hydrogen, but there's many other examples, calcium, ytterbium. When you collect those atoms and think of in a vacuum and at relatively low pressures, you can actually use laser pulses, represented by the red lines here, to address those atoms, to perform operations on them. And what you're really doing is you're pumping energy into them that causes these electrons to change their orbits. Just like we were talking about in the very beginning, that quantized structure now becomes a handle upon which to use electrons as qubits. Now, there's alternatives such as superconducting technology in the top right. Those superconductors we were talking about earlier can actually be fabricated into lines and other geometric shapes. Depending on the conditions, you can actually capture a pair of electrons. These are called Cooper pair. They not only correlated with each other, but they become an important way of encoding those zeros and ones that we were talking about. And now, instead of using laser pulses to address them, you actually use electric fields and microwave fields in order to tune the state of that circuit that drives them into their different superpositions, their different points on that sphere we saw earlier. Photons are a third opportunity. Here you're actually using the individual particles of light. They are the smallest amount of energy that you can have, but that comes in many different varieties, many different frequencies. There's other qualities such as polarization that can be used to address and manipulate those things. What's remarkable about photons is they're the fastest qubit alive. Nothing moves faster than the speed of light, and in this case, you can actually encode quantum information and send it over long distances. That becomes an incredibly powerful way of trying to communicate quantum information, and as we'll talk about a little bit, to secure how you talk. And then finally, the fourth example is the case of neutral atoms, which is very similar to the case of the ions that we talked about earlier. You're capturing individual elements, individual atomic units, but now you're causing them to interact with each other in a way that performs information processing, that manipulates their electrons and rotates them on this sphere that we were looking at. So these are kind of cartoon examples of all the technologies. What I would emphasize is that there is a very extensive research effort going into the development of these systems. This is just a gallery of different technologies that are under development by different companies. This, of course, is supplemented by an extremely broad research community, which is looking at alternatives to these technologies as a way of finding the best route to try to do quantum computing and other types of information processing. You can see the ion traps or the superconducting systems, the neutral atoms down here at the right, the photonic systems on the left. All of these technologies are in a relatively early stage of development. Even 40 years is a short amount of time when it comes to creating something so radical and so different. The challenges here oftentimes relate to the ability to control those atomic units, those individual packets of light, the electromagnetic fields and other types of controls, the precision necessary in order to pinpoint them and make them do what you want. But there's been a remarkable success along the way. In fact, over the last 20 years, we've seen a steady growth in the number of qubits that have been created through these different technologies. You can see at the mark where it says today, 2025, we're somewhere around the 1,000 qubit threshold. Now, I will say that the quality of those qubits isn't always the best. There's a wide variety of metrics that we can use to characterize them. But when you look to the right of today, to the next 20 years, 10 years, you'll actually see that there's continued growth in this technology, both in the number of qubits that are available, and we anticipate in the quality of those systems as well. That's an important metric for us, an important way of evaluating the readiness of the technology to make impacts on not just what we want to do scientifically, but what we want to do in terms of its applications more broadly. One of the key concerns, and this was alluded to by Rob in the introduction, is when does quantum technology surpass our conventional approaches? We've talked a little bit about the distinction between them. Bell's test gives us this radical way of confirming that quantum mechanics is real, but it doesn't necessarily tell us what that gets us back. This diagram is one of the ways we think about how quantum computing may actually change our approach to solving certain problems. The blue line that you see on here is just a sketch of how much time it would take to solve a problem. Let's say it's a chemistry calculation, just to be specific. As the size of the molecule that I'm trying to simulate gets bigger and bigger, the problem size here on the x-axis, I actually consume more and more time to solve that problem, both the time I spend processing it as well as I spend trying to understand its outcome. A quantum computer, though, by all accounts, will be much more efficient at solving these problems. Remember Feynman's quote that if we build these quantum computers, they're going to be the best platforms for tackling these problems. So that raises the question, where's the crossover? Where does it become best to use a quantum computer to solve a problem that today we use a laptop or a high-performance computer for? For the last, I would say, 20, 30 years, we've been well to the left side of this crossover. The number of qubits that we've had available have been too small to solve problems that are to the right of the crossover. But that's starting to change. In the last 4 or 5 years, we've seen publications, results from people doing studies on these quantum computing systems that suggest we're now getting to sizes between the 100 and 1,000 qubit mark that can actually rival the types of high-performance computing systems we have today. At Oak Ridge, we actually have the world's, well, until recently, we had the world's fastest supercomputer. We kind of tick-tocking back and forth with other institutions. But that becomes our high bar for measuring is a quantum computer really useful. And we've seen multiple tests now where the quantum computer is rivaling the capabilities of the classical computer, of the HPC system. And that's an important inflection point in the development of the technology and the implications, the mysteries that it has for us. Let me just kind of emphasize this. There's been a tick-tock going back and forth between the United States and China in the development of a particular type of calculation that's known as random circuit compiling or sampling, random circuit sampling. And what you're seeing on this graph is a function of time, how hard it was to solve the problem that these quantum computers did if we were to use a classical computer. In this case, it was actually the Frontier system at Oak Ridge, the high-performance computer. And it's been steadily increasing. That's just like I said a second ago. What I want to point out, though, is the y-axis is 2 logarithms. That's a doubly exponential growth in the power of quantum computing relative to our classical computing systems. Now, this particular type of problem turns out to be highly specialized. Not very many of us would ever want to do randomized circuit sampling in our daily lives, but the truth is it's an indicator of the type of progress that's being made in the technology relative to the progress that's being made in our conventional approaches to solve this problem. There are some other applications, though, that have far more greater significant impacts. One of these was developed by an algorithmist known as Peter Shor back in the 1990s. And the algorithm that he created was an algorithm to factor numbers. So if I give you the number 15, I would ask you, what are the factors? And you should reply 3 and 5, because multiplied together, they give you 15. As numbers get bigger, it becomes far more difficult to do that calculation. And in fact, much of the modern cryptography that we use, including in our cell phones, our bank accounts, and other platforms, depends on the fact that when you and I exchange factors, no one will ever be able to uncover what they were. In fact, for typical key sizes in modern encryption, we're normally around the 2,000 bit mark, which is somewhere there between 1,000 and 10,000. You can certainly make it larger if you want to. And it would require millions of years to crack those systems on our conventional computing systems. But Shor and his algorithm indicate that quantum computers would drastically reduce that time, so that today's modern key size is something that would be resolved or cracked in less than a minute. That's an important implication, because that means that all of our security in this modern infrastructure, our ability to protect information about ourselves as well as other people, is suddenly vulnerable to the advent of a quantum computer. And remember, these things are increasing doubly exponentially relative to our conventional approaches. But I will point out one very important detail, that as of a few years ago, the largest number that had been demonstrated to be factored on a quantum computer was only 3 bits. I've not changed my password yet. I haven't moved my money out of the bank account. I still feel comfortable with this. But it's an indication that in the long term, the implications of these technologies are going to be significant, much in the same way that our ability to understand atomic materials led to the creation of new weapons of mass destruction, new pathways to technology and energy. Quantum computing and all of its associated quantum technologies have a similar impact. They're radically disruptive, and they're not entirely sure what the long-term implications will be, both on how we protect ourselves and our information, but also all the opportunities that it provides us over the next 100 years. Now, there are many different applications out there. Factoring is a niche application. If you're not working for a security agency, you're probably not paying attention to it. Working at a science agency, I spend most of my time thinking about chemistry and materials and high-energy physics, and there we know what are the types of problems and algorithms we'd like to use on these systems. We're still pretty short of the types of qubits and their fidelity needed in order to solve, say, a simple chemistry calculation like we were talking about earlier. We can do toy problems, but getting to the point that we're to the right of the crossover, that we've reached quantum advantage, as they say, still going to take some more work, both in the development of the technology as well as the refinement of the methods that are used to solve these problems. This, of course, has gained a lot of attention, not just within the United States, where we have established a national quantum initiative, but around the world in the development of new national initiatives that are looking to advance the technology. Here, we've prioritized science. That's the thing that we need to lead with first. We need to understand the fundamentals of what quantum science is. We need to develop the workforce That's the ability to educate people, to raise awareness about this topic, but also enable them to have an impact in its development. The creation of industry and infrastructure, and ultimately the economic security and the international cooperation that will be significant for such an important topic. My role in all of this, working with the Department of Energy at Oak Ridge National Laboratory, is to lead one of its 5 national quantum information science research centers. These are focal points that have been established within the nation in order to coordinate our efforts around key topics, things that we think are distinct major challenges to the development of these ideas. I won't read through all of them. I'm happy to talk about any of them later, but I'll call out the Quantum Science Center on the far right, which is the one headquartered at Oak Ridge. Here, we're focused on the development of new materials that we think could provide us ways to scale up the number of qubits so that we can tackle that problem of reaching a crossover on some fundamentally significant applications. That means doing things like creating these materials, characterizing them, ultimately learning how to fabricate them into new devices, like the pictures that we were looking at earlier. What you're seeing here is part of a molecular beam epitaxy machine. It's actually laying down materials at atomically thin layers in order to stack them on top of each other and create novel structures that otherwise wouldn't have been created. I actually like to refer to it as the octagon because it has 8 arms coming out of that big metal ball in the middle. But in addition to creating new materials, we have a host of new technologies that are available today, including the ion traps. This is one that our colleagues over at the Quantum System Accelerator create. What you'll notice here is that that is a gold-plated surface. Those are the electrodes in which we're actually capturing the individual ions. The bright blue line that you see going across is superimposed on this image, but those are individual ions that have been caught in this trap and are being lit up by these laser pulses shining on them. The ability to move those ions back and forth, to interact with them with lasers, is allowing them to actually perform quantum simulations on these small but fundamentally unique types of devices. The infrastructure we talked about earlier is very different from the computing and sensing and communication systems that we use today. At SQMS, one of the other 5 centers, they've actually created what they call a quantum garage. This is something that outfits with the latest dilution refrigerator technology, control technologies, and the idea is that you bring in these new materials, these new chips, and you test them out. You see if you've got a better solution to solving these types of problems. It's an important part what we as the 5 centers do because it enables new pathways to discovery that can not only rival what's going on already and disrupt the pathways to what we call scalable quantum technologies, but also spur innovation and the creation of new ideas that we wouldn't have thought of otherwise. One of the things that I focus on is the integration of the quantum computers with our current infrastructure. So this is the Frontier supercomputer at Oak Ridge. It's actually made out of GPUs, interconnected together in a network. You can see the cables in the back. What happens if I connect the quantum computer to the high-performance computer? How do they actually talk to each other? How do they actually perform calculations in tandem with each other? That's probably the best outcome, not trying to rival one versus the other, but instead merge them together, converge the technologies, and create a new hybrid paradigm that crosses both the quantum and classical domains. And then, of course, there's the applications. This is a great example of chemistry problem. What you're seeing here is a cartoon of nitrogenase, an enzyme which is known to be essential in nature for the conversion of nitrogen into ammonia. Now, ammonia has many uses, but one of the most fundamental is for fertilizing plants. Nature figured this out a long time ago, whereas humanity is still trying to catch up. If quantum computers could give us insight into how these types of complex chemical reactions happen, we'd actually be able to create ammonia more efficiently, create food more efficiently, and lead to greater security of our global food supply. Again, one of those small changes has a huge impact on many different topics. And then, of course, I'm looking at the high school students in the back a lot right now, and It's just reminding me of how important it is for all of you to be aware of these changes in our scientific paradigm, because the convergence of these ideas is opening up new opportunities that, frankly, no one else has ever seen before. Mastering the language and the understanding here will enable us as an entire society to push forward the idea of how we create new technologies and what they can be used for. And in the end, my own vision is that there'll be a network of all of these ideas together, perhaps even something as clever as using quantum satellites that can transmit signals using those photons we talked about earlier to distant locations on the planet. Those can then be connected with each other in order to share this quantum information and perform more good for the world at large. That could include things like the intersection with artificial intelligence. We've already talked about how quantum computers can both accelerate our ability to process information. There is also the possibility that they can reduce the overall energy cost. Moving individual electrons around is about as energy efficient as you can get. This, of course, leads into the logistics and scheduling and planning operations, financial security, and of course, improvements to medical imaging. So let me just have one last word, and I'll wrap up. I hope what I have at least revealed are that there are mysteries, both in the understanding of what quantum physics means to us as scientists, but also the implications that it has on the convergence with information theory. We're already seeing some of these changes happen. We've got technologies like lasers and MRI machines that have opened up new opportunities. But in addition to that, there's an entire new paradigm awaiting with quantum computers, quantum sensors, and quantum networks that remains to be explored. So I hope this at least entices you to be mindful of the fact that the distinction between information and physics is not always so clear, and that their convergence is actually a powerful paradigm for us to use in the future. Thank you very much.
Right. So we get other questions? Right. So we're not. So folks in the desk.
He'll bring you the microphone.
Is the energy skates of the electron not limit how many points on the sphere you can do? The fact that there's only defined energy levels, does that not limit you to certain orbits?
Yeah, great question. So this goes back to the sphere we were talking about earlier that defines the qubit, and then also the fact that atoms themselves have these discrete levels, the orbitals that we call them. In this case, it depends on what you choose to encode your qubit. If you use the orbitals, then you can actually create superpositions of the orbitals, and the picture of the sphere that I showed becomes a little bit transformed. Many times, people are using the spin state of the electron. So electrons have a unique property that they're spinning in, let's say, the up direction or the down direction. And that becomes a really convenient way to talk about 0 or 1. And in that case, the ability to create a superposition corresponds to aligning that spin in any of the directions on the sphere. So you're absolutely right that the choice of encoding in the material system will have a huge impact on how you want to think and discretize the states of the qubit.
Maybe I'll ask follow-up. Yes. You showed quite a few different ways to code information, physical manifestations. Do you have an idea as to which one is ultimately going to be the winner?
I love this question. So I've got two answers. One, they're all winners. And what I mean by that is that when you look at our technologies today, we're not so siloed into a single technology paradigm. Yes, we use a lot of silicon, but the truth is we've functionalized those devices to many different things: CPUs, memories, GPUs, transmitters, network interfaces. So this idea of functionalization, I think, hasn't happened in quantum yet. We're already seeing some, let's call it trends in the behavior of these systems. The superconducting circuits are some of the fastest for operations. Those sound like very good CPUs. The ion traps actually have some of the longest coherence times, so those sound like very good for memories. Nothing can rival photons when it comes to transmission, so if I'm communicating or trying to move data around, they seem like they're the favorite approach. So my thought is in the future, it will be a heterogeneous system that combines all these together. That's my first answer. My second answer is none of them, because we've yet to discover the approach that actually will intrinsically scale up. In much the way that silicon follows Moore's law and has kind of had this ability to economically become very large scale, the quantum systems don't have this yet. So we may need a fundamental breakthrough in the materials or other types of methods that we use to create these qubits. But for now, we're learning a lot from the ones that we have available.